Hi, welcome back to our machine learning course. In the previous lecture, we saw the basics of how to build convolutional neural networks. Now it's time to break out PyTorch and start building them ourselves. First of all, I'm going to start with giving you some guidelines on how to build them in practice. Right, so first of all, we want to have not one, but multiple convolutional layers. So say we have an input image. We want to have multiple convolutional layers. Before we actually gonna feed that into a dense layer and then an output layer. 0, 1, 2. Classification for instance, right? So we want to have multiple convolutional layers. Why? Because the first layers are gonna learn simple patterns like edges and endpoints, while the deeper convolutional layers, they will learn how to combine those simple patterns into more complex patterns that are useful, so that at the end, the last convolutional layer has learned the big things to look for so that we can classify an image as being one of the classes that we want to identify. We want to have in between, we want to have max pooling layers to, first of all, increase our set of fields so we can make sure that every output filter has seen every part of the input image, right? So that allows us translation invariance. We also want to have, remember that every convolutional layer has, say it has 3x3 filters. One is not enough. One will just identify one kind of pattern, like a diagonal line, right? So that's not enough. So we want to have multiple convolutional filters in every convolutional layer. Say maybe the first one has 32 filters, which will allow you to find 32 kinds of simple patterns in the image. Right? If this number is too low, then you will only, let's say if this is 4, you will only be able to identify 4 simple patterns, and then if your image is more complicated than that, then that's not enough, and you will never be able to learn what you want to learn, right? So you have to have sufficient filters early on in the convolutional network. Deeper in a network, you want to have more. So maybe this convolutional layer has 64 filters. This one has maybe 128 filters, and this one maybe has 256 filters. The deeper network, the more filters you want to have. And it has to do with maintaining the number of activations, because every time we run a convolutional filter over an image, the output we get will be a smaller if this is like an n by n, maybe this is like n divided by 2, n divided by 2, and this one will be even smaller, and this one will be even smaller. And so if we're not careful and we're not increasing the number of filters, then we decrease the amount of information that flows to the network. And so if I plot this a little bit differently, then maybe this is a n by 1 output. After one convolutional layer, maybe this is like n divided by 2 by n divided by 2 because of my max pooling here. But since I have 32 filters, I do have 32 outputs as well, right? So this was n by 1, now it's n divided by 2 by n divided by 2 times 32. The next layer, maybe it's even smaller as n divided by 4, but now I have 64 output channels, right? So every time my input gets smaller, I increase the number of outputs to make sure that the total number of activations is sort of more or less equal. It doesn't have to be exactly equal, but more or less. We don't want to lose so much information because that's all the information I have left about my input image. Right? And so I want to make sure that I don't lose too much information. So that's why the deeper the network we go, we also want to increase the number of filters. If we have very deep networks, then we run into issues like vanishing gradients. So if we compute a loss here, we'll try a different color. If we have a loss here, we want to use that loss to update the weights for dense layer, update the weight of a convolutional layer, and update the weight of the previous convolutional layer, and so on. Right? What happens if my network is very deep? At some point, my gradients are going to diminish, and maybe there's only almost no gradient left at this point. And so I won't be able to update my early convolutional layers. So to avoid that, I can add a skip connection. Oops. I can add a skip connection between one convolution output, and I'm going to merge it with the input to another deeper layer, and by doing that also my gradients have now a path to jump, and so I can maintain my gradients deep into the network. Right. So we'll touch upon those things at their own time, but this gives you an overview of the different things we need to take into account when we design neural networks, convolutional neural networks. Okay, so first of all, what does it look like in code? So here we have PyTorch. There's a convolution, a very convenient function called conv2d. This is a convolutional neural layer, and we always have to specify two things. One is the number of input channels, and the other is the number of output channels. In this case, my input is a grayscale image, so it's one input channel, only the grayscale values. And the out channels, this tells me, oh, I have 32 filters. This is the number of filters I want to add to my convolutional layer. Right, so this convolutional layer takes one channel input and outputs a 32 channel output, and the kernel size is 3. Then I need some kind of, so the convolution itself doesn't have any non-linearities, so it will only give you linear model. So if you want to avoid that, you have to add a non-linearity like ReLU. Right? So after convolution, I add a ReLU. I add max pooling 2 by 2, and then another convolution layer, again ReLU, again max pooling, and another convolution layer. And what you can also see is that I increase my number of filters, right? So here I had 30 filters. Now remember, if my out channel is 32, this means that the next convolution layer has to handle 32 input channels, right? So this has to match the input of the next convolution layer. Now this convolution layer has 64 filters, so that's 64 here. Then the next has to handle 64 inputs, and this one has also 64 filters again. I don't need to overdo it too much, and that's the end of my model. Right. So three convolutional layers with max pooling in the middle, with ReLU activation, and starting with 32 filters, then 64, and then another 64 filters, and kernel size is 3. Okay. Here we can see what the output is. So now we can actually start looking at the output shape to see what the model is actually doing. So we started off with a single channel output, right? And I started out with a 28 by 28 input image, quite small input image, right? And after the first convolutional layer, what happened? Well, I now have a 26 by 26. I lost the edges because I didn't do zero padding, right? So I lose 1 pixel each side. But I have now 32 output filters. Yes, so let's do that again here. So it's 26 by 26 by 32. This is the output tensor after my first convolutional layer. And this guy has 320 parameters. Why? Because I have a kernel of 3 by 3 plus a bias, that's 10, times 32 filters. So that's total 320 weights. And this is the output shape of my tensor. Okay. The next convolutional layer does max pooling. So max pooling reduces my resolution from 26 by 26 to 13 by 13, and I'm going to lose the outer border of pixels again because of I don't do zero padding. So my next one is going to end up being 11 by 11 times 64 filters or channels. And now I have 18,496 weights. Right. And that's because, the overall formula is here. So it's kernel science squared times number of input channels plus 1 bias times number of output channels. So I had a 3 by 3 kernel size, it's 9 times number of input channels, 32. Remember that we had my kernel always has to match the number of input channels, right? So if I have 32 input channels, my kernel also has to be 32 input channels deep. Yeah. Okay. Oh, I lost the thing. Okay, start over. So I had, 11 by 11 by 64. And now I had, yes, so I had 32 channels before, so it's 32 channels times a 9 by 9 kernel, so 2 by 3 kernel, plus a bias, and then that 64 times. To draw it differently, I have a 3 by 3 kernel. This has to work in 32 channels. So it's not 3 by 3 by 3, it's 3 by 3 by 32. And I have 64 of those guys plus a bias every time. And it gives me 18,496 parameters to learn. So this is the activation tensor. This is my kernel. Right. Okay. Next time I again do max pooling. I lose my border again. So my next tensor is going to be 3 by 3 by 64 channels, and it's my final output of my convolutional part, right? So later on I will have to flatten this into one flat vector, and then I give this to a dense layer, and then this goes to my output layer. Okay. Great. So now we've seen how the original input image is transformed into these and these tensors. And we've also seen how we can compute the number of weights that are inside the kernels that we need to learn. Great. Okay, now to classify images, like I said, we have to first flatten my tensor, my 3x3 by 64 tensor, into one large flat vector. Then I add a dense layer, linear layer with relu. The size that you can choose a bit, but in this case we'll choose one which is about the size of my last tensor, so I'm going to choose 64 by 3 by 3. It's a safe choice. So it's the input, sorry, it's my input of my linear layer, and my linear layer itself has 64 hidden weights. That's not a massive reduction, so that's fine. And then my output layer has 10 outputs for the 10 numbers 0 to 9, and this has to match the number of outputs of the previous layer. Okay, and that's it. That's my entire model. Top to bottom, that's everything we have. And so in total we have about 93,000 parameters to learn, and now we can try that. Especially the flattening here. Yeah, that adds a lot of weights, right? Because we're basically doubling the number of weights we had at the ends. There are ways around that. One thing we can do is global average pooling. So instead of flattening my entire output tensor, which adds lots of weights, right? Because this gives me a very large output layer, and then we have to have all the connections with my next dense layer. This will add a lot of weights. Instead, what we can do is we can take every channel of my output, and we're going to take one number, the average, as the output. Right? So drawing this a bit differently, remember that we have a kernel like this, which is like n by n, like 3 by 3 by something like 64. To give you an example. What global average pooling does, it takes every channel, so every 3 by 3 slice, and gives you one output. Then take the next slide, next output, next slice, next output. And so what will happen is we'll have a 1 by 64 output. And then the next layer, say the next layer is a 64 dense layer. Okay, now we only have to learn 64 by 64 weights. And it's a lot less than actually flattening this into a 3 times 3 times 64 flatten layer, and then having to learn all the weights between this guy and 64 hidden neurons in the next layer. So global average pooling is very useful. I think every model since VGG uses global average pooling. You lose some information about the image, but remember what the output mapping actually does in the last layer. It should light up if certain patterns are in the image, but where they are doesn't typically matter so much. Right? So you don't lose so much information by taking the average of them. One exception of that is something like object detection. So if you have to detect where in the image an object is, then you construct it a bit differently. In that case, the position might matter. In that case, you should not use global average pooling. But for typical classification problems, this is totally safe to do, and so it's almost always a better solution than just flattening all your activations at the end. Okay, now we replaced our flattened, remember this was our flattened situation, just a flattened layer, gave us 93,000 parameters. Replacing this by an adaptive pooling layer, now we only have 56,000 weights to learn. Okay, that's it. Now we can train this thing, and so we train this on ImageNet, so this is a very simple data set, and we find that we get 99% accuracy, which is slightly better than our previous dense architecture, which had 98% accuracy. Now next, after MNIST, which is a very simple example, we want to try something that's a little bit more real world, and we're going to use the cats and dogs data set. So it's images of cats and dogs. It's much more realistic. They're color images. The objects, the cats or the dog, can be in any part of the input image. They're not nicely centered, not nicely cropped. So it could be the cat taking up the entire image. The cat could be a very small part of the image. It could be multiple cats in the image. It can be good lighting. It can be bad lighting. It can be shadows. There can be dogs looking in different directions, right? So a lot of variation. So we're definitely gonna need more data. We're going to need a more complex model, and we're going to have to do a little bit more work to actually build a working model on this. First of all, we have to do more pre-processing. These are not tensors, these are JPEGs. So we have to first of all decode the JPEGs into tensors. We're gonna have to do rescaling. We have to resizing that they're all the same size, because that's not always given, right? And afterwards, we will get out our images like this, all the same size, but still, and all normalized, but still quite difficult to learn, right? Okay, the data loader, I'm going to use PyTorch lighting, which allows me to build a data module again. Yep, so I'm going to set my transformer. So this is going to do only two things. It's going to resize the image to 150 by 150, and it's going to convert it to a tensor. Nothing else for now. My data set is going to take data from a folder. This is the path to the folder. I'm going to every image in the folder. I'm going to apply my transform pipeline. I have a train data set and a validation data set, and with these I'm going to create data loaders, which will return to me the data into batches of a certain batch size, which is 20, and it's going to shuffle the data every time during training. During validation, of course, I don't need shuffling, so I set it to false. Right, that's my data loader. My model, I have to make a little bit more complex before. Remember, before we had 3 convolutional layers of filter sizes with first of all 32, then 46, then 46 filters. I'm now going to have 4 convolutional layers, and I'm going to double again the number of filters. So here the third layer has 128 filters, and also the fourth layer is also going to have 128 layers. I could do more, but my data set is not that large, so I'm going to keep it now for now to 128 filters, also in my last layer. Of course, I'm going to do adaptive average pooling at the end, 1 dense layer, 512. My output layer can have only 1 neuron because it's cats or dogs, right? So I'm going to predict the probability of cat. If it's close to 1, then it's a cat. If it's close to 0, it's going to be a dog. Okay, so 300,000 parameters to learn in total. I'm going to start my trainer. I'm going to run it for 20 epochs. I'm going to, of course, use my GPU. I'm going to set the deterministic to true, which means the random seed will be fixed, so I can reproduce the same experiment. And I'm going to add 2 callbacks. One callback is the metric tracker, which will just store the validation loss and training loss and the validation accuracy and train accuracy, so I can draw a learning curve later. And I'm going to add a checkpoint callback for logging the weight, so I can store the model weights so I can reload them later. The model checkpoint value very useful to keep your models stored. It's a very simple thing you can add. You can tell it to monitor something like the validation loss, and then it will save only the best model it encountered in terms of validation loss. And that is the path where it will store the model and the name of the file where it will store the model. Okay, so if we run that, then okay, so not too bad. We get up to validation accuracy, up to 80% accuracy. But you can see one very big problem here right away, right? Validation loss goes to 0. Sorry, training loss goes to 0. Validation loss, not so much, and goes up at the end. This is a clear sign of overfitting, right? So you want to address that. Different ways to do that, but one thing that's we can do is first of all to generate more training data. Right? So we're going to do something called data augmentation. We're going to generate more artificial data based on our original data, so we have more training data to work with. We also add regularization like dropout, batch normalization, L1, L2 regularization. And later on we're going to also not start from scratch, from random weights. We're going to start from pre-trained weights. And so we will explore all those things in the rest of this lecture. Okay, first of all, data augmentation. So we're going to take our original input image and we're going to make variations of each input image in such a way that it still represents more or less the same image. So the idea is to create more data that conceivably would also have occurred in a larger data set. So if I would simply have taken more images of my cats and dogs, those images might look as what we are building here. Okay. So what are we doing? We're going to update our transform pipeline. We're still going to resize, that doesn't change. But now we're going to add random rotations. So we're going to take our input image, we're going to rotate it by a few degrees. And so every rotation of the image could be a possible new input, right? So before we actually give the image to be put into a batch, we're going to rotate it a little bit. And every time we see the same image, we're going to randomly rotate it a little bit differently. That means the same input image will appear differently in different batches. Every time rotated a little bit differently. We're also going to resize this a bit. We're going to make it a little bit smaller, a little bit larger. We're going to zoom in or zoom out a bit. We can do our horizontal flip, like a mirror image horizontally. We're also going to add shear. So shear actually is a simple operation where we go from, let's see. Yeah, so instead of having, if this is my input image, what I will do, I will push the pixels of the top part to the right and the bottom part much less, right? And this will transform the image as if, yeah, the top part is like pushed aside and the bottom is held on the floor, right? And that's another way we can generate more images which are a bit different, but yeah, not too weird, hopefully. Up to 20%, so we don't want this to be too much. If we rotate too much, yeah, then you can have like a cat which is like this, which is probably normal, but a cat that is like rotated 90 degrees, maybe that's less normal, right? So you don't want to do it too much. And then because I have different lighting conditions, right? Remember, for instance, this image here should have very different lighting than this image here. We can also play with lighting with something called color jitter. So we're going to play with the brightness. We're going to make it 20% brighter or less bright. We're going to increase the contrast a little bit, or we can decrease the saturation a little bit. Okay. So after doing all the things, we're going to transform it to tensor and then normalize again, and that's going to be our new set of images. So what does it look like? Like this. So you can see that these are all taken from the same input image, but every time we sample this image, we will give a different result. Maybe this is the result for the first time we have the image in a batch. The next time we encounter the image in a batch, we use this one, and so on, right? So every time before we put an image into a batch, we will augment it a little bit. Right? It's going to be rotated a bit differently. It's going to be flipped, or it's not going to be flipped. It's going to be more saturated or less saturated. It's going to have more contrast, less contrast, and this will act like if this was just this all valid input data, which is not. It's artificial, but it's probably going to be useful training information for the model to learn that this is a dog, this is a dog, this is a dog, this is also a dog, right? And conceivably, you could have seen a dog that looked a little bit more up or down than the previous time you saw it, right? So that's data augmentation. Okay, we could also add dropout at the end. And we're also going to add L2 regularization. It's called weight decay in the edit optimizer. It's not shown here, but we'll just do it in the code. And now we see before, remember we had this rampant overfitting, right? So we were not learning after a while. With data augmentation and a little bit of dropout, we now learn a lot better, right? Right, and that's it for now.